Imagine a mysterious object lurking in the universe's shadows, the dark twin of black holes called gravastars. Are they just theoretical curiosities, or could they be the ultimate cosmic game changers? Today, we're about to unlock a cosmic secret that could change everything you thought you knew about black holes. Brace yourself for a mind-blowing journey into the unknown, where science fiction becomes reality. To understand gravastars, we first need to revisit the life and death of massive stars. When stars significantly more massive than our Sun exhaust their nuclear fuel, they die in spectacular supernova explosions. During this process, the core of the star collapses under gravity's relentless pull in less than a second. The outer layers explode outward, shining with the brilliance of entire galaxies. Post-supernova, the star's core faces one of two fates. It either becomes a neutron star, an incredibly dense object composed mostly of neutrons, or it collapses further into a black hole, an entity so dense that its gravitational pull prevents even light from escaping. But what if there's an alternative? A third, even stranger possibility has been proposed: gravastars. Introducing the Gravastar. Coined from gravitational vacuum star, the Gravastar concept suggests that, instead of collapsing into a singularity, the core of a dying star transforms into a bubble of pure energy. Imagine a cosmic soap bubble, filled with an intense concentration of energy, encapsulated by an ultra-thin shell made of an exotic form of matter. This shell is unlike anything we've encountered naturally. It's so dense and tight that stretching it by just 1 meter would require the energy equivalent of a supernova. This shell isn't made of atoms as we know them. Instead, it's composed of a new, unique form of matter at the absolute edge of physical possibility, so extreme that it defies our current understanding of material science. The interior of the Gravastar is a perfect vacuum, but one filled with an unfathomable density of vacuum energy. An ocean of fundamental energy that's billions of trillions of times more concentrated than the vacuum outside. The nature of the shell. One of the most astonishing features of a gravastar is its shell. Despite being only a fraction of a nanometer thick, it is incredibly tight, cold, and dark. The coldest object in the universe, just a billionth of a degree above absolute zero. To put this in perspective, even the cosmic microwave background radiation, the afterglow of the Big Bang, appears brighter in comparison when observed in deep infrared. How can matter be that cold? The answer lies in its composition. The shell isn't made of ordinary matter. It's a form of extreme, exotic matter that exists at the boundary of what physics can produce. Its strength and density are so immense that attempting to stretch it would require energy on a scale only seen in supernovae. The interior. Inside the shell, the universe's fundamental fabric is in a state of super dense vacuum, a space where the energy density of the vacuum itself skyrockets. In our universe, particles like quarks, electrons, and photons are waves in an omnipresent cosmic fluid, the vacuum. When a star collapses violently, this vacuum becomes compressed, pushing all the way to the limits of what physics allows. This compressed vacuum is not empty in the traditional sense. It's filled with immense energy, creating a mini-universe within the Gravastar. The energy density inside is so colossal that it's almost impossible to comprehend, billions of trillions of times more concentrated than the vacuum outside. Yet, thanks to the shell, this incredible mass is confined, preventing it from expanding uncontrollably. How do gravastars differ from black holes? From the outside, gravastars look remarkably like black holes. They curve spacetime intensely, trap matter and light, and generate the same gravitational effects that make black holes so fascinating. If you were to fall into a gravastar, you would experience extreme gravitational forces, likely being torn apart before reaching the shell. Upon crossing the boundary, your atoms would disintegrate and your matter would be converted into vacuum energy, adding to the core's intense energy reservoir. However, a crucial difference is that gravastars lack an event horizon. Black holes possess an event horizon, a point of no return beyond which nothing can escape. Gravastars, on the other hand, have a physical shell that acts as a tangible boundary. This shell could, in theory, be observed indirectly, offering potential evidence for their existence. The significance of cold, massive, and dark. Another intriguing aspect of gravastars is their appearance. Their shell's ultra-cold temperature and darkness make them virtually invisible in most wavelengths of light. Only in very specific observations, like deep infrared imaging, might we detect their presence. The shell is so cold that it barely radiates heat, and since it's made of exotic matter, it doesn't emit light like normal matter. This extreme darkness is why gravastars are often thought of as the dark twin of black holes. They mimic the gravitational effects, but differ fundamentally in their structure and properties. Theoretical implications and the search for evidence. The idea of gravastars isn't just science fiction, it's a serious scientific hypothesis. They solve many of the paradoxes associated with black holes, particularly the issues surrounding singularities and information loss. In a black hole, the core collapses into a point where physics as we know it breaks down, leading to the infamous singularity problem. Gravastars avoid this dilemma by replacing the singularity with a shell of exotic matter, preserving the laws of physics. Moreover, gravastars could explain some astrophysical observations that don't perfectly align with black hole predictions. For example, the collision of two gravastars would produce gravitational waves with subtle differences compared to black hole mergers. Instead of a simple thump, the gravitational waves might produce a gong with echoes lingering, a signature that scientists are actively searching for with instruments like LIGO and Virgo, a cosmic enigma. Gravastars represent one of the most captivating frontiers in modern astrophysics. As enigmatic, dark twins of black holes, they embody the tantalizing possibility that the universe harbors objects even more exotic than we can currently imagine. Whether they are real or merely mathematical constructs, their study pushes us closer to understanding the true nature of space, time, and matter. The universe continues to surprise us. With each discovery, we peel back another layer of cosmic mystery, inching closer to answers about the fabric of reality itself. Gravastars remind us that the cosmos is a place of endless wonder, a realm where extreme physics and imagination collide to forge new possibilities.